So let me begin. I will spend just a few minutes to review where we were at the end of the last lecture. And then if you have any questions about the last lecture, please either write them in the chat box, or if you want, you can just ask them orally. So you can think of these questions. So last time we are focused mainly on Maxwell field, and we saw that to talk about radiation, the best way is to consider a conformal completion of Minkowski space. In order to do this completion, we use some coordinates, and there was one nice question which said that, well, but this all depends on coordinates. And the point is that I just did that for pedagogical reasons. We really do not need to introduce those coordinates, as we will see today. But basically, what we need to do is to go far away from the sources. But now in the general curved space-times, there are no radial coordinates, and the distances are defined by the metric, which is the dynamical field itself, like what the Maxwell field was in the Minkowski space. And the second problem was that what looks like time-dependent or wave-like or dilatory, oscillating in one coordinate system may appear to be time-independent in another coordinate system. And there is a very famous example, so-called Levi-Civita metric, for which there was a lot of confusion about whether there is actually gravitational radiation. And this was settled that there is gravitational radiation in this paper long time ago by doing a conformal transformation and attaching Scri and looking at the structure. But because this is very subtle, there was a lot of confusion in the early days about even the reality of gravitational waves. This may sound shocking to most of the students, knowing that gravitational waves have been detected, but Einstein had derived the quadruple formula already in the 1916 to 1918. So that actually does have gravitational waves, and it tells you how much energy is carried away by gravitational waves in terms of the third time derivative of the quadruple moment. But this was done in the linearized approximation, and there was a lot of confusion whether gravitational waves exist in full nonlinear general relativity. And as we're going to see, Einstein himself contributed to this confusion. And today what we're going to do is that how this was finally clarified in the 1960s and 70s by groups of Bondi, Sachs, Newman, Penrose, and many other people. And that is what we're going to discuss in the next two lectures. So are there any questions? So there is one in the chat box. So let me just look at it. No, I guess I don't see any question. Are there any questions? I'll wait for 1 minute. If you are typing questions, please type them, or you can just ask them by switching on your mic if you can.
Professor?
Yes?
Last Saturday, a student asked me how did the peeling condition, peeling properties derived the first time.
So, how were the peeling properties derived?
Yeah. At the beginning.
Yeah. So in the Maxwell case, we saw how they were derived, right? In the Maxwell case, we got a physical space-time, and we got a Maxwell field, and we got a null tetrad in physical space-times, N, L, at Scri plus the peeling property was here. The null tetrad is N, L, M, and M bar. And these are the various components. These are just definitions. The Maxwell field has 6 components, and these are 3 complex combinations of those components. And because the Maxwell field is smooth at scribe, because F hat AB is equal to FAB, and F hat AB is in a conformal space-time, and the conformal space-time scribe is just at a finite distance. And so if you have some source doing something, then at a finite distance, everything is perfectly well defined. So we know that F hat AB is perfectly well defined, but because of conformal invariance, FAB is equal to F hat AB, and then F hat AB times this combination is what is called phi 2 naught, and therefore phi 2 naught is well defined, but the physical space-time phi 2 is related to phi 2 naught by phi 2 is equal to phi 2 naught divided by R. Phi 2 naught is perfectly well defined at null infinity, and therefore we conclude that the physical phi 2 falls like 1 upon R. Similarly, the physical phi 1 falls like 1 upon R squared, and the physical phi 0 falls like 1 upon R cubed. And these are the peeling properties. And the most important for us are these two. This is the radiation field, which falls like 1 upon R. And this is really the real part of phi 1 naught. That is really the Coulombic field, and that has a charge. And this was the exercise that we had last time, at the end of last time, to show that the electric charge is given by this particular formula. Is this okay? Okay. So now let me just begin with the with this today's lecture. And first, I want to tell you about this confusion. And the confusion arose because of the following. As I said before, in 1916 already, just a year after the discovery of Einstein's equations, Einstein basically repeated the calculation in the Maxwell theory. In Maxwell theory, if you have a time-changing dipole moment, in Maxwell theory, it is an electric dipole moment. And if it is time-changing, so dipole moment is a vector, and if it is time-changing, T double dot, then Einstein saw, it was well known that the square of this quantity is really the, it tells you how much energy is radiated by the electromagnetic waves. Einstein generalized that formula to showing that the time-changing quadruple moment in general relativity produces gravitational waves. But however, of course, he did it using Minkowski space and weak field in Minkowski space. So linearized gravity in Minkowski space. And as I said, that this was in parallel with Maxwell theory, where the field waves can carry away energy and momentum, whereas in Newtonian gravity, of course, there are no gravitational waves at all. So Einstein showed that linearized gravity is like Maxwell theory. But then, based on his working with Nathan Rosen, who is shown here, is a famous Israeli physicist, in 1936, Einstein sent a paper to Physical Review entitled, "Do Gravitational Waves Exist?" And the same day, he wrote to Max Born, the famous quantum physicist, saying, together with a young collaborator, Nathan, I arrived at the interesting result that gravitational waves do not exist, even though they had been assumed to be a certainty in the first approximation, in the weak field approximation, in the linearized approximation. This shows, Einstein says, that nonlinear gravitational wave field equations tell us more, or rather limit us more than what we had believed up to now. So he's saying that in the weak field approximation, he had concluded that gravitational waves exist, but if you take full general relativity, in fact, they do not exist. So Einstein submitted 3 papers to Physical Review in 1936, and only this paper was sent to a referee, and he received 8-page report, and now we know that the report was written by Robertson of the Friedman-Lemaitre-Robertson-Walker universe, and it showed that there was an error, not in the solution mathematics, but rather in their conclusion, because they actually confused a coordinate singularity with a physical singularity. And Einstein and Rosen had very curious reactions to this referee report. So Einstein just basically withdrew the paper from Physical Review, never sent a paper to Physical Review again. And Nathan continued to believe that gravitational waves do not exist until for several more decades. But finally, Einstein resubmitted the paper and appeared at the Franklin Institute. But between the two times, Einstein realized that there was indeed a mistake in the paper, and he changed the title of the paper, the conclusion of the paper. So instead of the previous title was "Do Gravitational Waves Exist?" he changed it to "On Gravitational Waves." And in fact, he reversed the conclusion, saying that gravitational waves do exist. And then he had the one example in full general relativity. These Einstein-Rosen waves. These are cylindrical gravitational waves, the simplest solution to Einstein's equations, which have gravitational waves. And the abstract of the new paper says a rigorous solution to cylindrical gravitational waves is given for the convenience of the reader. The theory of gravitational waves and their production, already known in principle, is given in the first part. And after encountering the relationships which cast doubt on existence of rigorous solutions for undulatority, oscillating gravitational fields, we investigated rigorously the case for the cylindrical waves, and it turns out that rigorous solutions exist. So he actually changed his conclusion. So the point of this was just to say that there was a lot of confusion about the reality of gravitational waves because of these coordinate effects in general relativity, and that was finally clarified by these people. So what I'm going to do now is to tell you about how this was clarified, but using the formulation of null infinity that we used for the Maxwell case. And this is really the definition first given by Penrose and then refined by Garrosh and me over several years. And the final definition is remarkably simple. So what we're doing is we're first of all defining what we mean by asymptotic flatness at null infinity. And what we're doing in this procedure is to really take the definition that we had at Scry, right? The definition of null infinity that we got here, that we can do a conformal transformation and attach a boundary to space-time, and that would be the null infinity. But the final answer does not involve any coordinates. This answers a question that people were asking me. One person asked me last time. And it says that if you are given a physical space-time, so let me just emphasize that I have changed the notation a little bit, because in this part of the talk, most of the time, we are going to be talking about the conformally rescaled space-time. So in order to avoid hats and such thing, the conformally rescaled space-time will have no hats. So it will be just G and M is the conformally rescaled space-time. So the physical space-time now, it has a tilde. So physical space-time M tilde G tilde is said to be asymptotically flat at null infinity if we can attach a boundary, which is called, as I told you last time, Scry, which is script I, and the topology of the boundary is 2 sphere times R, such that on the completed space-time, on this completed space-time, so we got the physical space-time and I've attached a boundary to it. There's a metric which is conformally related to the physical metric, which has the same signature of the physical metric, and such that this omega is actually smooth on Scry, on the manifold, on the physical space-time upside. It's smooth everywhere on the conformally rescaled space-time, but it's equal to 0 at Scry. So the boundary is given by saying that this conformal factor vanishes, which means that the physical metric is not well defined in the boundary, exactly as in the Minkowski space completion that we saw last time. And the conformal factor omega is 0 on the boundary, but its gradient is not equal to 0. This really captures the idea, if you go back to Minkowski space-time, that omega behaves like 1 upon r in the physical space-time. But of course, we don't have r here. So we just ask that this be true. And this condition then says that omega is a good coordinate at null infinity. So basically, we got the physical space-time. So again, like in drawing the picture as in Minkowski space, I got some physical space-time here. And I'm attaching to it some boundary, which I'm calling Scry. And on the boundary, omega is equal to 0 and grad omega is not equal to 0. And then there is an assumption on the stress energy tensor. We want to say that as you go to infinity, in fact, on the boundary, the physical stress energy tensor vanishes like omega to the minus 2. So omega to the minus 2 times the physical stress energy tensor is smooth at scratch. So this, of course, is equal to, by Einstein's equation, is equal to omega to the minus 2 times 1 upon 8 pi g times the Einstein tensor. And this condition is satisfied by physically interesting Maxwell fields that we saw yesterday, for example. You can check and scalar fields that because the field falls off at infinity, the waves and the Coulomb field fall off at infinity, stress energy tensor has a property that omega to the minus 1 times t tilde does have a limit. Now, this definition is so incredibly simple. No coordinates, there's nothing. And it looks like, what does it have to do with null infinity and scry and all that? And the beauty, and Penrose's definition, when he gave before, had all the essential ideas that I'm talking about, but it's a bit more complicated. There are several other conditions up here, and they all that have to do with null geodesics and so on, and they all go away here. For gravitational waves, we don't need those conditions, and this is the final form that I had obtained, but starting from Penrose, and then Garrosh already gave a simplification, and then this is the final form. And it is coordinate free. And it captures everything, as we are going to see, to discuss gravitational waves in full nonlinear general relativity. Now, just as intuitively, you can think of omega as 1 upon r of Minkowski space-time, just for your intuition. It's not necessary to do that rigorously. And of course, cry will be coordinatized by u, theta, phi, because you're going to have u, theta, and phi, and omega in Minkowski space where the coordinates, and omega is equal to 0, and therefore. So this is really for your intuition. It is not really needed anywhere in rigorous treatment. So in this lecture, I will assume, for simplicity, instead of saying that there is a stress energy tensor which dies at some rate, so that omega to the minus 2 times the stress energy tensor has a limit, I will just assume that this is 0, that t tilde IB actually vanishes in a neighborhood of scry. So we're not assuming that stress energy tensor vanishes everywhere, just near infinity it vanishes. And this is just for simplicity. You can do everything with this, but then the formula become a little more complicated. So just for that reason. And in the references I give you, this condition is not assumed. We just assume this condition up here. Okay. So for example, if you have a neutron star coalescence, then they also emit electromagnetic waves and gravitational waves. And in fact, this condition is satisfied in that particular case. But just for simplicity, I'm just going to assume that this is actually 0. Okay, just for simplicity. Okay, so here is a picture that how you can think about it. Here is some neutron stars, which are actually, there are 2 of them, and they're going around, spiraling, going around each other. And then they finally merge. And in this picture, they don't form a black hole, but just another neutron star, and that persists. This is this hypothetical picture, just for simplicity of drawing. And then what we have is this physical space-time is everything inside, and the boundary that I've attached is this. And of interest for us is the fusion at infinity, which is called scry plus up here. And then radiation is emitted along these red lines that we saw that are depicted up here. And then you get some waves at infinity, and this infinity is, as you can see, is a 2-sphere cross R. We got null infinity like that. And then on that infinity, you get waves. So you're producing these waves, and this is the waveform. The retarded time coordinate up here is going like U. We're going to introduce those things in a minute. And then that is a picture that you've got up here. And scry minus is here for completion. And we're going to have the notion of radiation, and then the idea that there is no incoming radiation, all the radiation is produced by sources, is going to be encoded by saying that the radiation field vanishes here, just as in the Maxwell theory. So what we're going to do now is really a simple example of how one can do this. And the example I'm going to do is Schwarzschild solution, just because of simplicity. You can do curve, you can do other solutions, but then the calculations are a little bit longer. But the statement here is that in the case of the Maxwell field, In the case of the Schwarzschild space-time in general relativity, there is of course no radiation, it is static space-time, but just to see how scry actually comes about. So it could be just a static star sitting here, and that produces the null infinity. There's no radiation in that case. So what we do is we take the so-called tortoise R star coordinate to be equal to R plus 2m minus 2m R upon 2m minus 1. And then we got here U is a retarded coordinate, and then the statement that then U is going to be given by T plus R star. I should have drawn here the explicit diagram. The explicit diagram for your reference that I have in mind is the one that you have seen many, many times. You've got this Kruskal space-time picture that you've seen many, many times. And I am looking at the right-hand quadrant up here. So here is a horizon, and here is the null infinity. And this is the horizon, future horizon, past horizon, and past null infinity. And that is the region I'm talking about, which is supposed to be the physical space-time, ds tilde space squared. And this R star coordinate goes to minus infinity on the horizon, as you know. But then what we can do is just define, this is the intermediate step. You just need to define the retarded coordinate U. So retarded U coordinate is going to be, so this will be the horizon, H minus, H plus, this is sky plus, this is sky minus, and the retarded coordinate is U, and that is just given by T minus R star. Then if you take the physical Schwarzschild metric and you write in terms of U R theta phi, where U is defined by this formula, then because U is a null coordinate, it can just becomes the 1 minus 2m over R times du squared minus 2 du dr plus R squared. So this is exactly like in Minkowski space. In Minkowski space, you did not have 2m, you had just minus 2 du squared. Now you got 2m up here. And now if you set omega to be equal to 1 upon R and rescale the metric, so this is a conformally completed metric, which is now well defined everywhere, including scry. So previously, the physical metric that I got here is not well defined on scry, but now the conformal metric that I'm defining, so the physical metric is not well defined, but conformal metric is going to be well defined and is given by just this. And at scry, omega vanishes. So this hat here just means equality that holds at points of scry. So on scry, this term goes away because of omega is equal to 0, and you get a metric which looks exactly like the Minkowski metric. So the metric at scry looks pretty universal. And what we're going to do, what we're doing up here is really going to scry along null direction. So actually, I really drawn that picture. Sorry about that. So the statement is that I'm looking at this corner, and I'm going to null infinity in the retarded direction, U equal to U naught. And then the statement is that you get this metric. So we've got a nice metric. We've got a nice metric here, which is well defined everywhere now in this quadrant, not on the horizon, but here it's completely well defined. In the future horizon also it is well defined, but the past horizon it will not be well defined. And this, but we're not interested in the horizon, we're just interested in scry, and there it is completely well defined. So here is an exercise, do all the intermediate calculations to show that this is the case. And an advanced exercise would be, you can also do it for the Kerr space-time by using, again, you can use Kerr-Shield coordinates if you like. That is the simplest way to do the Kerr in the Kerr space-time. So now what you want to know is that, okay, this is a definition which looks so simple, and how is the whole thing that I'm talking about coming out of it? Because so far we don't even know that scry, which is defined by omega equal to 0, is a null surface and various things. So how are they going to come about? Well, they all come about because of the field equations. The field equations we are assuming R tilde is equal to 0. The physical Ricci tensor vanishes. That is because I assume that T tilde equal to 0. As I said before, you don't need to assume that. You only need to assume omega to the minus 1 times T tilde be equal to 0 is well defined as scry. But at the moment, I'm just making my life simpler by just saying that we have got vacuum equations. Then the statement is that I got the conformally rescale metric, and this is the physical metric. And so this relation enables you to relate the Ricci tensor of the conformally rescale metric to the Ricci tensor of the physical metric. And the exercise is to check this relation. And if you need help, see Wald's book, Appendix D, where he does conformal transformations, and you can check that this is the case, that the physical Ricci tensor is related to the conformal, the Ricci tensor of the conformal metric by this particular formula, where the Ricci tensor of conformal metric plus omega to the minus 1, grad A, grad B, omega to the minus 1. So this is, of course, well-defined. Everything which is not tilde is well-defined at scri, because the metric G is well-defined at scri. But we can see here that I got factors of omega to the minus 1, and that says that, in fact, in principle, there may be a problem for R tilde AB. But we know the field equations, R tilde AB equal to 0. So this actually is 0. Even though there are apparent quantities which are blowing up, this is 0, which tells us that the coefficients which are multiplying them are highly restricted. So first of all, omega is equal to 0 at scri, and the metric G is smooth, and that has a strong consequences. Let us suppose that we set n to be equal to just GAB grad omega. This is also what we did for Maxwell field. And then, since GAB is equal to omega square times G tilde AB, the G tilde AB is equal to omega square times GAB. And therefore, if I were to contract this equation with G tilde AB, that is the same as on the right-hand side. I am contracting with omega squared times GAB, and GAB is perfectly well-defined. So omega squared times, I get omega squared times R, and here instead of omega minus 1, I get omega. And here, similarly, I get here contraction, and this, and I just get 12 times NM. So this is what survives, and the statement is that these two factors combine and give me 6. So this is the equation we get by just multiplying by taking the R tilde. But of course, R tilde is 0 in a neighborhood of scri, and therefore, and furthermore, since omega is equal to 0 on scri, we know that n is null normal, is a normal to scri, because grad omega will be the normal to scri, because omega is a constant, and so all I'm doing is raising its index. So therefore, Na is actually normal to scri. But now what we see up here is really that if I take the limit as omega goes to 0, this goes away, and I get NM is equal to 0. And therefore, we conclude that the normal to scri is actually is null. And if it is normal to scri, normal to surface is null, then that surface is null. That is the definition of a null surface. If the normal is time-like, the surface is space-like. If the normal is space-like, then the surface is time-like. And if the normal is null, then the surface is null. By the way, if in fact you are a positive cosmological constant, you can check that the same equation will tell you that NM is negative. That means normal is time-like, and therefore scri is space-like. And if lambda is negative, then scri is time-like. It is because of we are assuming lambda equal to 0, we're getting the conclusion that the scri is actually null. Now I can go back to this equation. I know that NM is equal to 0. So NM is the same term as this. This is equal to 0 at scri, but I still have omega minus 2, so I have to be careful about it. But I still multiply this equation by omega and take the limit. And you can just do it yourself. And then when you do that, you just find that if I multiply this by omega and take the limit, then this goes away. And this is just equal to grad A and B, because the grad B of omega is just equal to NB. And this all proportional to GAB. Everything is going to be well defined because we have this metric is well defined. And so therefore we conclude that grad AN is proportional to the metric at scri. And therefore, of course, just contracting, we can find out the proportionality factor. That must be grad ANB is equal to, sorry, this is wrong. This should be 1/4. I'll correct it maybe I'll correct it right now. That will be better. So I might forget. Equal to 1/4. It's equal to 1/4 of this 4, sorry, 1/4. Okay. So 1/4 of this is what I get up here. Grad ANB is equal to that. Now, however, we still have a freedom. You see, when we did this conformal completion, omega was not God-given. We say that space-time is asymptotically flat if there exists omega. But if there exists one omega, which is such that this is 0 and this is not equal to 0, then in fact, what I can do is I can just do a rescaling. I can multiply this omega by little omega, and therefore I get here a new conformal factor. And now what we need is this omega should not be equal to 0. So what we need is omega, whereas omega is equal to 0, is smooth and is not equal to 0 at sky. This will guarantee that grad prime A omega prime is not 0 at sky. So if grad omega is not equal to 0 at sky, then grad prime A omega prime is also not equal to 0 at sky. And that will be what will be guaranteed if in fact little omega does not vanish at sky. So we can always choose an omega. And now there's an exercise that I can choose an omega such that there's one omega is a free one function, and then I got here one condition that make this null normal to be divergence free at sky. But of course, if you make it divergence free, then by field equations, it was proportional to the divergence, and therefore I got this equal to 0. That means I can always choose a conformal factor. So we concluded two things. The first conclusion is that sky is a null surface. And the second conclusion is that we can choose a conformal factor, omega, such that grad omega is equal to 0 on sky. And this follows if you just make the n to be divergence free, and therefore this is called choice of conformal factor is called a divergence free conformal frame. Now just for simplicity of calculations, we are going to restrict ourselves to this divergence free conformal frame. You can always do that. But now we ask what is a restricted conformal freedom? It's like in gauge transformations, you always fix a gauge, but then say, well, how much freedom is still left over? Well, supposing I were to make another transformation, and I suppose now that this was divergence free to begin with, and the new one is also divergence free. Then it is very simple to check. This is the exercise. It's very simple to check, but it's not trivial. It will take you 3 or 4 steps. That this implies that ln of omega is equal to 0. In other words, omega is constant along. So if you think of sky as being a cylinder, then n is along this direction. And then the statement is that grad A of omega is equal to 0, ln of omega equal to 0 at sky. That says that omega does not depend on u. U is the affine parameter of Na, and it only depends on theta and phi. So in the divergence-free conformal frame, sky looks like a cylinder, and coordinates can be u, theta, phi, where u is just the affine parameter. Na dA is just equal to d by du. And theta phi, you can choose any one cross-section and introduce theta phi there, and just Lie drag theta phi, ln of theta equal to 0, and ln of phi equal to 0. And you will get u theta phi as coordinates, and then this is the thing that we got here. So you just choose a fiducial cross section. On that fiducial cross section, you choose on the fiducial cross section, you choose theta and phi as coordinates, and you Lie drag them. This is the same as ln of theta equal to 0, and this is the same as ln of phi equal to 0. So we can always include such coordinates. In other words, of course, we have to make sure that nothing depends on the initial cross section and so on. That's what we'll make sure. But it is used just intuitively. It's good to sort of think about functions little omega as being a function of just theta and phi intuitively, instead of all the way. The more precise statement is this, that this is equal to 0 on sky, but intuitively that just means it depends on the angles only. And so we'll often use that intuitive language because it is easier to grasp. Now in the literature, one often further restricts the conformal freedom. So I got this omega, and now I got omega equal to 0. Most of our discussion will not do that, but occasionally to make contact with the literature, we'll do that. One further restricts the conformal freedom by demanding that the metric that you will get, which is just the pulling back, the metric on sky is just the pullback of the space-time metric. I got here a space-time metric GAB, and I got sky as a boundary. And then I got the metric GAB up here, and I can restrict this metric to sky. That is called the pullback, and the pullback of the metric to sky is what is being called here QAB. And because sky is null, this QAB is going to be degenerate metric because it has a null normal, so therefore it has signature 0 plus plus. And this object up here, the QAB is a plus plus signature, And this is a QAB, therefore you can think of it as a metric on the two sphere, like this two sphere up here. And the statement is that given any two sphere metric, you can always make a conformal transformation by little omega to make the scalar curvature of the new metric to be constant. When that happens, you say that it is a unit to it's a round two sphere metric. And if in fact the curvature is equal to 2, the scalar curvature is equal to 2, then that is just a unit two sphere metric. In the Euclidean space, if you take a two sphere, r equal to 1, then you can calculate its scalar curvature and you'll find that the scalar curvature is 2. So you can always go to a conformal frame. If you start from QAB, you can go to Q prime AB such that this is actually 2 constant. And you can always do that. Solutions always exist. And furthermore, there is still a freedom. There's a 3-parameter high-media freedom. And this corresponds to the physical space-time choosing a time-lag vector. So this omega, the freedom up here is that this omega up here, in other words, if you wanted to put r is equal to 2 and r prime is also equal to 2, and the two metrics are related by this, you can do that. But this omega is very restricted, and these are just real numbers, alpha naught and alpha I, and this ri up here is just the usual unit radial vector. Sine theta cos, its components are sine theta cos phi, sine theta sine phi, and cos phi. And these numbers are such that minus alpha squared plus alpha I equal to -1. So these are like components of a unit time-like vector. So to summarize, the statement is that first, the consequence of the field equations is that Scri is null, and you can always make Scri divergence free. Once you do that, the restricted conformal freedom is just that ln of omega is equal to 0. Omega is a function only of the angles. And so we can do that always. And then the statement is that you can further restrict, if you wanted, the conformal factor. It's not necessary, but you further restrict it so that the QAB that you have got is going to be a unit two sphere metric. And such choice of conformal factor is called, we call a Bondi conformal frame. And there is advantages of going to the Bondi conformal frame because the metric is given explicitly some coordinates, theta pi, and it's like a familiar two sphere metric. But the disadvantage is that this is not unique, and you've got this rather complicated conformal freedom. So there is a pluses and minus. In most of the case discussion, we are not going to do this. We're just going to look at divergence-free conformal frame. So we're just going to assume that grad A and A equal to 0 at Scri, which means grad A and B of Scri is also equal to 0. That is by field equations, Einstein's equations. And then the restricted conformal freedom is just equal to this. Okay, and now what I would like to do is to just tell you very quickly a relation to the older literature. In the older literature by Bondi and Sachs, and then also by Newman and his collaborators, Newman and Anti, they did not really use a conformal completion. They give you coordinate expansions, which to begin with look a little bit complicated. Right? That looks a little bit complicated up here. And so as we'll see in a minute, the coordinate expressions are a little bit complicated. But the statement is that supposing we're given a conformal completion, as I have done up here, from there we can introduce coordinates. And this was again answer to the previous question. How do you introduce these coordinates? We can as follows. First of all, here is Scri that is given to you. And what I can do is I can take any cross section of Scri, as I told you before, and we had introduced here theta and phi coordinates. And I got also the affine coordinate of n. I just choose one. So that is an affine coordinate, the coordinate u. So I got u here and theta and phi. But right now, in this framework, what we're going to do is to introduce coordinates also in the interior. So what do we do? So supposing you give me some cross section. So this is a new input I have to put in, and that is why the coordinates have some certain amount of arbitrariness. But you can check that everything you do doesn't depend on this choice of the initial cross section. But if you choose the initial cross section u equal to u naught, then you can define U equal to U1, U equal to U2 cross sections, because U is just given by ln of U is equal to 1. That defines U coordinate everywhere. And on each of these cross sections, N is already a null normal to this cross section, but every null vector, every two-sphere vector, every two-sphere submanifold has two null normals. One is that way, and the other is the null normal future directed will be that way. So what I do is, instead of looking at the future directed one, I look at the past directed one, because that will go in the space-time. And then what you do is, we are just going to use this LL, and I'm going to use a geodesic. So I'm going to ask that LA grad A LB should be equal to 0. So just propagate this along geodesic. After a while, the geodesics will cross and the coordinate system will break down. But in the neighborhood of infinity, this coordinate system is okay. Remember that from the physical point of view, neighborhood of infinity means R greater than some R naught, say. So it really is infinite. R can take any value between some large R naught to infinity. So it's really a lot of freedom up there. I mean, there's a huge region there. So in that region, the statement is that I'm going to get coordinates. So I got U theta phi here, and I got this null geodesics. And what I do is I just drag the U coordinate, the theta coordinate, and phi coordinate by just asking that LL of U equal to 0, LL of theta equal to 0, LL of phi equal to 0. So I get U theta phi here because I got theta phi and U, and I'll get them along this cross section, along this null cone, along this null cone, etc., etc. So in this whole neighborhood near scribe, I get coordinates which are going to be U theta phi. And of course, I already have the coordinate omega, and I can just set omega to be equal to 1 upon R, just definition of R. And therefore, I got coordinates R, theta, phi, and U. So I can, given a conformal completion, I can introduce these coordinates, and then you can check. And so I should have written here explicitly that this is an exercise that you can check that this coordinate condition tells you that this construction tells you that in fact you will get some expression of the unphysical metric or the conformally rescale metric GAB, and then G tilde AB is just equal to omega to the minus 2 times GAB, or is equal to R squared times GAB. And then you can check that in this coordinate system, the physical metric has a form minus du some function times du squared, another function times du dr. And then I get the other terms, which are really these xa's are the theta and phi coordinates. So xa just means theta phi. So capital A, capital B always will take values 1, 2. I don't need to introduce such notation, but it is somehow, it's very common in the literature, and it might be useful for you. So I'll just do that. So QAB up here is just sorry, this should have been Q tilde AB. It's a unit two sphere metric. And then I got these functions F1, F2, and then I got other functions here which are called HAB. So that this is a 2 by 2 matrix. Therefore, it has 3 components here. There's a 1 component here, 1 component here, and here there are off diagonal pieces, and A goes from 1 to 2. So I got 2 components. So I got 2 plus 3 plus 1 plus 1. So I get here 7 components up here. And so this is a form of the metric that you can easily show just starting from a conformal completion. So these are 7 functions, but you still have some coordinate freedom because I just chose omega to be equal to 1 upon R, but I can still have this freedom. Omega goes to omega prime, which is equal to little omega times omega. And I can use this freedom further in order to eliminate one of these functions. And there are 2 choices, one made by Boddy-Sachs and Newman-Unti, which are written here. I'm not going to go through them right now, but just I will, if there's time at the end, I will go through it. But I will also send these notes so that you can look at them. Okay, so this is the statement that we can have 2 statements. First is that you got a definition of asymptotic flatness. It's an incredibly simple definition of asymptotic flatness up here. And given this definition, you can conclude that the null boundary scri is null. The boundary scri is actually null. And then you can always use a conformal factor so that grad A in B is equal to 0, that you can just show that, and we are going to use in this such divergence-free conformal frames. And then the last remark is that we can really get the expressions that people told us in the literature. So now we can come to the last part of, which is really what is the radiation field and what about peeling properties in the exact general relativity. So this is really like what we're doing for the Maxwell field in Minkowski spacetime. The more important thing is that where is the radiation field? What do we mean in a gauge invariant manner by radiation? So again, we fix the asymptotically flat spacetime and we fix the conformal completion where Scri is divergence free. So this is true. Now, if I calculate the Riemann tensor of the conformally rescaled metric, then it's just an identity that Riemann tensor can be written in a trace-free part, which is the wild tensor, and a trace part, which is Ricci part. And this S up here is just RAB minus 1/6 RGAB. So this is just an identity that you all know, I hope, from differential geometry. There's nothing to do with physics. It is just Riemann tensor can be just expanded like that if given any metric GAB. So it doesn't have to do with any Einstein's equation or anything like that. And now we bring in field equations, and the free field equations are going to say that the physical Ricci tensor is equal to 0. So R tilde AB equal to 0. And R tilde AB equal to 0 would mean S tilde AB equal to 0. So S tilde AB equal to 0. And again, we just convert S tilde AB in terms of the SAB. This is exactly what we had done just a while ago for the Ricci tensor. And I'm just doing this, we had done this for Ricci tensor. And now I'm just doing it for RAB minus 1/6 RGAB. So we can just relate the physical ones and the conformally rescaled ones. And when we do that, so you obtain this formula up here. And this is again an exercise. And again, you can look up Wald's Appendix D to see the conformal transformations. And now what I do is I multiply this equation by omega, and I take the curl of this equation. By curl, I mean I take grad A of this equation, SBC, and I am skew symmetrized over A and B. Okay. So when I do that, I just find, so this is an exercise. From here, I just will find that omega times grad S is plus CAB, CD, and D equal to 0. But of course, therefore, on Scri, if I take the limit to Scri, because of this omega, this goes away, and I find that most of the wild tensor is equal to 0. So almost all of wild tensor is 0 in the sense that wild tensor plugged with n is equal to 0. And now there is a more difficult part, which again, if we had half an hour, I could prove this to you, but we don't have so much time. So it is in the literature that if you use Bianchi identity and the fact that Scri has a S2 cross R topology, then that just implies that in fact the full wild tensor is equal to 0. As a remark, I just want to say that this subtlety arises only because we are using the cosmological constant equal to 0 and Scri is null. If we had cosmological constant positive or negative, then this condition immediately implies wild tensor without equal to 0, without referring to topology or Bianchi identity. It is straightforward exercise. But when Scri is null, it is important to realize that there is a subtlety, and we really you have to use this topology of Scri and also Bianchi identity. Now, if in fact wild tensor is 0, in our case the metric is smooth, and anytime a field is 0, then it means that omega to the minus 1 times that field has a smooth limit. This is just the L'Hopital rule of calculus. So omega to the minus 1 times the wild tensor, which is called KABCD, and that has a smooth limit to Scri. And this is often called the asymptotic wild curvature. And this is in contrast to the Maxwell field, because the Maxwell field, remember what we had was that in the present language, the physical FAB was the same as the rescaled FAB. Whereas here, the statement is that this is not the case. we really had this factor of omega to the -1. The wild tensor itself actually vanishes at scry. And now, therefore, at scry, what I can do is the following. I can take this object, asymptotic wild curvature, which is omega to the -1 times c, and I can plug in two null normals. Again, it's an invariant construction because I got scry, and scry has a null normal n, because if you give me a conformal completion, it comes with a null normal, and it comes with a metric G, whose wild tensor I can calculate. Therefore, I can calculate this, no coordinates, no tetrads, nothing is required up here. And therefore, I get this K, A, B, C, D. Now, this object is symmetric because of symmetry of the wild tensor, and I'm plugging in N and N. I'm symmetrizing on A and C. That makes it symmetric in B and D. So it is symmetric. It is transverse in the sense that if I take KBD times ND, NB or NB, I get 0 because I already have AC, and wild tensor is antisymmetric in AB and CD. Therefore, this 0. So it is transverse. It's symmetric and it's traceless. It's traceless because it's a wild tensor. Wild tensor is traceless. This is just a traceless tensor. And therefore, if I take GAB times KB, I will just get 0. Therefore, I got symmetric, transverse, traceless, and you can calculate the two components of this, and you can easily show that it has precisely two components. And furthermore, these two components, we just saw that KAB times NB is equal to 0. Therefore, these two components are really the angular components only. And therefore, we can, if you want, we can write it as EAB. So these two components are the same as its angular components. So which I'm just defining a new field. I call it KAB if you like, but then it might be confusing which K I'm talking about. So I call this EAB. So in the case of Maxwell field, what we know is that FB is FAB times NA. I can define a quantity FB, which is FAB times NA. And I can pull back this F, just like I was pulled back this up here. And again, it has only two components because it is perpendicular to N. And on scry, I got N and then theta and phi, or N and M and M bar. So this really can be expanded out in terms of M and M bar. And therefore, these two components you can write as EB. And this is exactly the radiation field phi 2 naught. So the statement is that in full general relativity, I'm telling as a fact that these two components are in fact the radiative modes in exact general relativity. And just as in Maxwell case, instead of talking about E, people usually talk about a complex scalar rather than talking about a vector or a one form. So similarly here, instead of talking about symmetric second rank transverse tensor, people like to talk about some scalar field. So what do I do? In Maxwell case, as we saw before, we can just take F times M bar, and that was precisely the phi 2 naught, and also I can calculate a real part of phi 1 naught in a similar way, but that will be a little bit later. Let's not worry about it. Let's just look at it here. And the statement is that this is a quantity that I have up here. And in gravitational field in exact general relativity, one follows exactly the same procedure. And we define psi 4 naught instead of phi 2 naught, psi 4 naught as just take the radiation field, which is this K, and plug into it M bar and M bar. Here we are just plugged into it just one M, because I had only one component. Here I got two indices, therefore I got M bar, M bar. This, of course, depends on the choice of M bar, and I got two M bars. This depends on choice of M bar, and I got one M bar, and therefore it is supposed to, in the Maxwell case, it is in the Maxwell case, it is supposed to have spin weight -1. If there is one M bar, it is -1. If it is one M, it is +1. And now here I got two M bars, and therefore one says that it has got a spin weight -2. So psi 2,4 is object with two M bars, and the same as spin weight -2. And this is called the radiation field, and these are the two null the components. And finally, I can introduce the physical tetrad by just conformally rescaling exactly as we did in Maxwell case inside the space-time. And you can check here very quickly that if I take the physical wild tensor, so this should have been, If I take the physical Wild tensor and I calculate these things, then you will find that in fact it is just equal to psi4 naught divided by r. So again, as in the Maxwell case, the radiative mode falls like 1 upon r here, exactly as in the Maxwell case. So this is it. Last time we saw how null infinity gives us the two radiative modes naturally, and now we see that in Maxwell, in a full nonlinear general relativity using SCRI, you can also extract the radiative mode. And in numerical relativity and approximation methods and the waveforms and so on, you'll always find people talking about the psi4 naught as the key quantity from which the waveform is constructed. So I should stop, and if you have, we have about 5 minutes. So please, if you have any questions, ask them either using the microphone or just using typing the message.
Professor, I have a question. It's as the right and here the EAB is what's EAB? EAB is the electricity part of KAB.
Yeah, so the statement is I'm calling it E because of the following. That supposing you are given, I mean, it's electric, but it's electric with respect to, it's electric with respect to the null normal n, right? It's electric. It's electric with respect to the null normal n. So normally, if you take a space-like surface up here, in Minkowski space, you usually take a space-like surface and you get a time-like normal up here, and the usual electric field is given by FAB and B. Okay, so it is you're contracting it with a not NB. Sorry. The usual electric field is given by TB. So electric field is given by FBA times TB. Okay, it's contraction here with this quantity up here. So, but here we got null normal to the surface. So it is like the electric field, if you like, but it's the electric field with respect to the null normal. And the same thing is true here. I'm contracting with two nulls. So therefore, this is like the electric part of the Wild tensor. But usually, again, electric part of the Wild tensor is defined by doing this C, A, B, C, D. And then you take TATC up here. And you could say that that is equal to the electric BD. But here, it's really the null normals. So it's a little bit of misuse of the terminology, or rather generalization of the terminology. So in a more generalized sense, it is like the electric part of the Wild tensor. But you should keep in mind very strongly that it is with respect to the null normal.
Okay, thank you. Is the magnetic part of where tensor contributes to the radiation?
Yes, so what happens is that because you got normally the electric and magnetic part, EA and BA, if I have a space-like surface, they are independent. And there are 6 of them. Sorry, the FAB has 6 components, and they are contained in the 3 EA and 3 BA. Okay, but here what happens is that with the null normal, what happens is that if I take FAB and B, and if I take star FAB and B, and I call it the magnetic one, okay, if I do this, then this, and this is the first was electric, then the statement is that the E and the B, as so defined, they are not independent from each other. There are many components to be the same. So as a result, I can also take the magnetic part and construct similar quantity, and that quantity would also be will have radiation. So I can use either the electric or the magnetic part and plug into 2 ends in the gravitational case and 1 end in the Maxwell case to get information about the radiation field. But I think so some of the things that I've references I've given will explain this better. I'm a little bit not explaining full detail, because what you really have to do is to take star KAB upstairs. So you start with KA. Sorry, let's start from scratch. You have to start really with upstairs KBD to be equal to star KABCD, NB, and A and C. And then this will be what you might call the magnetic part, B, A, B, B, D. And then this will also have the same information, radiative components as this quantity has. So with null surfaces, you have to be a little bit more careful, but you can use either of them. But for these lectures, I'm going to stick with just K with downstairs indices, and that is what is going to give you the.
Okay, thank you. So
yeah, we're a little bit late, but maybe if other questions, other students have questions, please ask if you have questions. Would it be useful, students, just write yes and no in the mailbox, in the chat box, please. Several of you, just say yes or no. Yes, if you think in the beginning of next time, we have some time for questions so that you can think about what we had done in the first two lectures and ask the questions. Or if you're understanding most of the things, then say no. Yes means yes, we should have time for questions in the beginning. No means we don't need a time for questions. So please write. It will take you 1 second. Okay, so a few more responses, please. Yes, no. You have to cooperate with me. I'm putting in a lot of work in this lecture, so I need some feedback from you in order to improve them. Yes, no. Yes, okay. We need to digest this lecture. Very good. Yes, okay. So next time I will begin and you can ask me any questions you have on the first two parts that we have done, and then we will continue. Okay, thank you.